Good morning. We are 100% in prepare for midterm mode. We got a midterm coming up here in a couple days, and so here are the review problems. I hope you guys are getting an early look at this, or that you've already have taken a look at some of the problems that we're going to be going over today. It's a good representative set of problems. You guys also have the homework problems, and you have the lecture examples that we've gone through. But this is a nice way to see what a previous semester's midterm looked like, and that's what these are. So let's get started. So here is one of those midterms, and there's 4 problems, and it's broken down into parts A, B, C, D, just like our midterm was, our first midterm was. And so let's look at this first problem. It says that we have an object. There it is right there. It has a mass of 12 grams. It has a charge of 17 millicoulombs. And it's coming in with some initial velocity, 40 meters per second. It's about 100 miles an hour. And there's an electric field region that we've set up. We're going to use that electric field region to redirect that object. So as that object goes through the electric field region, it's going to get accelerated in some direction. Now, because the E field is directed, let's say call this the Y direction, velocity starting out in the X direction, what's going to happen is this is a positively charged object. It's going to get pushed in the Y direction. So let's take a look at how we're going to set that up. So here it is. Mass m, velocity v naught. I've converted those into standard units. That seems like a good idea. The electric field here is 9,000 newtons per coulomb. And so I'm going to start off and say, hey, if I'm going to say, find out what the acceleration of this object is, I'm going to need to know what the force is. Now the force, the electric force, can be calculated by taking the charge and the electric field. In this case, we just have the one charge, but we have this already existing electric field. That's how we're going to calculate the force. So what I want to do is take Q times E and pay attention to units. And it looks like what we've got here is a force of 153 newtons. Now that force is going to be in the positive Y direction. The acceleration is going to be in whatever direction the force is in, and the force here is in the vertical direction, and so the acceleration will also be in that direction. So that's what those little diagrams are showing. The vector direction is positive Y. When we divide through by the 0.012 kilograms, we get this really large acceleration. It's a fairly good-sized force for such a small mass object. So 12,750 meters per second squared, and yeah, we can get these really high accelerations in these electric force problems. So now again over there it's saying that the electric field, the force, the acceleration, they're all in the same direction. Now the second part of this, once we found out magnitude and direction of the acceleration, is saying if this length is 10 centimeters, what will the velocity look like when the object exits that region? And so let's take a look at this. I'm going to need, in order to calculate velocities, let's look at this first. So the Vx here, well, that's not going to change, right? This is kind of like gravitation, where we threw something horizontally off a cliff. And then the X direction did not change, but the Y direction gradually did. And by the way, I should point out that we, unless are specifically told to include gravity, we don't. So we don't need to include gravity on these electric force problems unless we're specifically asked to. Now, if we did include gravity, if this is near Earth, the gravitational field is going to be about 9.8. 9.80 meters per second squared. That's not very big. compared with the acceleration we have due to the electric force. So if we did include gravity, it would have a negligible effect in any case. So again, the Vx is going to stay constant. There's no forces in the x direction, nothing to speed it up or slow it down in the x direction. So it's going to stay right at 40. Now in the y direction, what's going to happen is there's a constant acceleration in the y direction, and that says as time progresses, the velocity will get larger and larger. So I'm bringing out some equations of constant acceleration. Now I'm going to need to find out how much time this object is in the region. You know, it's a short distance, it's only 10 centimeters long, and the thing's moving 100 miles an hour, right, 40 meters per second. And so it's going to be a very short time that it will undergo that acceleration. Now it's a really large acceleration, but it's only going to last for a short amount of time. So that's what the diagram at the top is showing also, is what we're expecting is we're going to get this parabola shape up to that point where it exits the field, and then it will go into straight line motion again. And at that point it will have x components and y components, and that's what we're in the process of solving for. So the time can be calculated by looking back in the x direction and saying, look, in order for this object to travel through here, I can take the distance in the x direction and divide through by the velocity in the x direction. So the amount of time that we'll spend in the electric field looks like 2.5 milliseconds, 10 to the minus 3 seconds. So that's a really short time period. And plugging that into the velocity y equation, we end up with 31.9 meters per second. So there you go, enormous acceleration over a very, very short period of time, and just those few milliseconds, the object picks up 31.9 meters per second. Now we can get a magnitude on that by squaring components, add them together, and take a square root using Pythagorean's theorem. And then the angle we can get by doing an inverse tangent. And that works out to be 38.6 degrees. So that's it. So this is something that was in chapter 21. You guys are thinking, yeah, it's like everything was in chapter 21. That chapter had a lot of stuff in it, and it did. But this is definitely one of the things that we want to emphasize in the course is we want to be able to follow objects that have charge, follow them through electric fields. Okay? And at some point we're going to add magnetic fields in, but that's a few weeks away. So for right now we'll stick with the electric fields and follow charges through the electric fields and see what happens to their velocities. Now they didn't ask about position, but I thought why not? So I picked the point where it enters the electric field as being the 0, 0 point, x equals 0, y equals 0. And by the time it has crossed through to the other side, well, it's gone 10 centimeters, right? So that's kind of a built-in number that we were already given. Now what we can do is we've got the amount of time, this 2.5 milliseconds, so that says that we should be able to find out how far has it deflected. We know the angle. We're going to get the angle that it's traveling at by looking at velocity components. But down here below, what I thought is, you know, how far has it traveled then in the y direction? Is it still within the region that we've set up? So plugging the number in for the time, now this time it's t squared in that really large acceleration. I ended up with, well, I got it in meters and then I converted it into centimeters. I got 3.98 centimeters, or about 4 centimeters, as its y coordinate position as it exits. So that seems kind of plausible, right? If this is 10 centimeters long, maybe it's, I don't know, what does it look like, 8 centimeters wide? So that would be just enough deflection that it maybe just misses the edge over here or something. We could imagine that maybe it just misses the edge, or maybe it just hits the edge as it gets to the other side. So accelerations, those are going to come from looking at the forces. Those are going to come from looking at the electric fields. And then once we get the accelerations, then we're back in chapter 3 mode. You know, we're going back to chapter 3, keeping track of components, keeping track of accelerations, velocities, and displacements in x and y directions. All right, let's move on to problem 2. There it is. I guess we should read it from here. This is actually, so this picture goes with problem 1. I hope this makes sense. This picture goes with problem 2. It says that we have some concentric metal spheres. So we're going, they're conductors. So we've looked at problems like this, and we found that for conductors, any excess charge or any depletion of electrons or any excess electrons, the buildup tend to be at the surfaces. So we're already guessing that, well, for example, I got a plus Q charge on that inner metal surface, and it's got an inside and an outside too. So there's four surfaces we got to be keeping track of here: inner surface and outer surface of sphere number 1, and then inner surface and outer surface of sphere number 2. And combined, inner and outer on that sphere number 1 is going to have a combined charge of Q, plus Q, and the outer one is going to have a combined charge of minus 2Q. Now what they're asking is, let's find the electric field everywhere, within the inner sphere, between the spheres, outside the sphere, and then for each of the spheres, determine the location of charge. Now, the electric field within the conductor itself is going to be 0, and we're going to use that in the problem. So here it is. I've identified 5 regions, A, B, C, D, E, and I started out by saying, hey, region B and region D, there will be no electric fields inside a conductor. So those are taken care of. I'm sure I'm going to get some partial credit for writing that down. So for regions B and D, the electric fields will be 0. For regions A, C, and E, we can use Gauss's law. So there is Gauss's law written down for a sphere, and we've done Gauss's law in enough examples now. The spherical examples are the best, because we don't have to approximate anything. We can get these exact formulas for the electric fields in those cases. And so I'm taking the E field times the surface area of a sphere, and that little r is a variable. So that little r is going to enable me to imagine different locations, A, B, C, D, E, and 4 pi k q enclosed for each. So this is how I calculate the electric field. And so again, if I go into region, well, I guess we haven't looked at A yet. If I go into region A and draw the Gaussian surface inside there, there's no charge enclosed. So the electric field inside will be 0, and that's a statement telling us that because the surrounding charge, there is surrounding charge, but it cancels exactly. Because the electric force, the electric field, drops off exactly like 1 over r squared, and because surface areas increase exactly like r squared, it turns out that those 2 effects lead to Gauss's law, which tells us that the electric field is 0 everywhere within region A, not just at the very center, but at all locations, exact cancellation. Now, moving on to region B, once we're inside that conductor, the electric field needs to be 0. I guess we'll leave that. We'll come back to regions B and D. So I guess we're going to jump ahead to region C. So if I move into region C, I will have an enclosed charge of Q. And so all of these are enclosed charges. Enclosed charge A, enclosed charge C, enclosed charge E, and write in a little enclosed here and here. And that tells us that in region C, the electric field is kq over r squared. In region E, it's going to be negative kq over r squared. So by the time we're out in region E, we are going to have enclosed all of the plus q and all of the negative 2q. So if we go back to look at, see, there was negative 2q out here, plus q here. If we're looking at a location out here, and drawing in a Gaussian surface, that enclosed charge is going to be negative Q. All right, so that gives us the electric field at all locations. Now in part D, it says determine where the charge is located. And again, because it's a conductor, we can think of that inner sphere, or maybe I'll call it sphere 1, and the outer sphere, I'll call that sphere 2. They each have an inner or an outer surface to them. Now, what we can say then is, look, if I'm inside the conductor, the electric field is going to be equal to 0. So here, yeah, so what we have to make sure is that within region B, there is not going to be any enclosed charge. And the only way we can make sure that that's happening is to make sure none of the charge is on the inner surface. So Gauss's law being used kind of in reverse to tell us that there will be no charge on the inner surface. Now, when we move to the outer surface, what's going to happen at the outer surface is all of the charge is going to go to that outer region. And so whatever is not on the inner surface needs to be on the outer surface. So that tells us that all the charge necessarily is going to end up on the outer surface. Moving on to region D, again, everywhere within region D, the electric field will be 0. So the enclosed charge needs to be 0 within region D. So if I'm looking at region D, I know that I've already got this plus charge on that outer surface of sphere number 1. Something's got to cancel that out. And what we're going to use to cancel that out is a negative charge on the inner surface. So that plus Q and those negative Q go together. Now finally, on that outer surface of sphere 2, we've got a total charge of negative 2Q. Negative Q has gone to the inner surface. Whatever charge is left will go to the outer surface. And so the outer surface will be negative Q. All right, that's what that looks like. So Gauss's law, again, it's a powerful technique to determine electric fields, and this is an example of determining how the charges are going to arrange themselves. As long as we have a lot of symmetry, we can make some pretty strong statements, powerful statements about the electric field and where the charge will be located. All right, let's move on and take a look at any of these. If you guys have questions on this, stop by office hours and let's get those questions looked at. And you can always do that right away. You don't have to hesitate. So I have office hours, a good number of office hours set up that you can stop by. So on problem 3, we've got a stick, this one-dimensional extended charge. It has a length of L and it has a combined charge of Q, and that Q is evenly distributed along the length. Now it's not a conductor. It's in order to have uniform charge on a stick, we're going to have to have it be an insulator where we've placed charge and it's being held in place all the way along this. Now there's a distance r here from the end of that stick of charge out to some point. Oh, that's point P. It's usually point A, but this time it's point P. So there is a point P out here, some distance r away, and we want to come up with a formula for the electric potential. Now notice here that we've got to pay attention. It could be asking about electric field. It could be asking about electric potential. This one's asking about electric potential. Let's take a look. And so for this, here is the setup. So what we've done here is I've identified the stick of charge. Oh look, I did call it point A. I switched over and used point A for this. Now at point A, there's going to be a potential, dV, and there's also going to be an electric field, so I drew that in. Now it really only asked about the potential. We could have asked about both, I think that would have been a more sensible thing to do, just to let you guys know. And, but, you know, the problem itself really only asks about the potential, so I think that's all we're going to solve for right here, although we could take a look at electric fields and see how that would be done also. So what we're going to do is we're going to go back and say, look, to find the potential at A, what we're going to say is each little segment, each little point charge along the length of that charged stick is going to make a contribution at point A. And its contribution will be given by K dq over R. So every little bit of voltage, every little bit of potential, is equal to K dq, every little bit of charge, divided by the distance. Now, I could have switched this into X, and kind of a toss-up here. I went ahead and left it in terms of R, but we could have switched over and used X as a distance, right? Everything here is lined up in the X direction. Now, if we were calculating the electric field, the direction would be an important part of the problem, but we're not. We're calculating potential, and remember, potential is a scalar. We don't have to keep track of components. So I just have to make sure that I have a good way of representing the distance R. Now, I can start at point A. I could integrate from left to right along that stick of charge, or I could integrate from right to left. It really doesn't matter. So what I did was this. I set the problem up in a way where I started at the lower value of little r, which is big R, and then I integrated from R to R plus L. So I didn't use an XY coordinate system. I just worked, in some sense, I'm measuring distances from point A back to different locations where the charge is located. And I plugged in dq as q over L dr. Now that's going back to the idea of uniform charge distribution. If I take the total charge and divide by the total length, that will give me a length per distance, and that's the factor that relates little bits of charge with little bits of displacement. All right, so we got a kq over L coming outside, and we're left with dr over R, and we've got the limits of integration. So I think we're pretty well set here. Let's go ahead and carry out the integration. When we carry out the integration, we get an ln of R plus L minus the ln of R, and you know, when you subtract natural logs, those become the natural log of the ratio of those two numbers. And so that's it. That's our answer. I could have imagined adding some more onto that problem. We could have calculated the E field. We could have done that a couple different ways. We could have taken a derivative of the voltage function. We could have put an X coordinate system, an XY coordinate system in here, and kept this as some kind of variable and taken a derivative to find out what the electric field is. Okay. We could also have put some numbers in. I guess that's another thing that we didn't do in this example that could have been included. All right, let's move on to problem 4. And so problem 4 looks something like this. I've got this battery, I've got a switch, I've got a bunch of capacitors, and the way the switch is set up is when the switch goes to the left, so if we throw the switch to the left, then we're charging capacitor 1. And that's probably going to happen pretty fast, right? So we put the switch to the left, capacitor charges up, we can find out how much charge is on there. And then what we're going to do is we're going to take the switch and move it to the right. Now when I move that switch away, I've stored up that charge. There's not a way for the charge to return to the battery. You might think that this plate on the capacitor here, some of that charge can disappear, but it can't because the battery has no way to store that charge. So unless we return equal amounts of positive and negative charge to the battery can't store it. So the capacitor is going to continue to store that charge, and then when the switch goes in the opposite direction, that's going to enable some of that charge to migrate over to this double capacitor system. Now we've looked at how to combine capacitors in series, and it sure looks like capacitor 2 and 3 are in series, because when we're charging them, they're both going to acquire the same amount of charge. They're going to start out with no charge at all, and then they're going to build up charge, and they're going to have to build up the same amount of charge each because they're in series. Now, capacitor 1 is not in series with the other two. In fact, we're going to need to treat capacitor 1 as being in parallel with the other two. This capacitor was already charged, so it's not charging with 2 and 3. And when we throw the switch, capacitor 1 is going to end up sharing its charge. And the amount of charge that migrates over to this right side in the circuit is going to depend on when the voltages balance out between the two sides. So once the charges have migrated, once we've reached equilibrium, then the migration stops, and at that point the voltage on the right side will match the voltage on the left side. Those are the conditions that will enable us to go in and figure out how much charge is on those capacitors. So here we go. Here is the battery. Here we are in the first part. Now I've taken that circuit that we drew and I've just divided it into two parts. Initially, when we're charging a capacitor 1, capacitor 2 and 3 are out of the picture. There's no way those can be charged. They have one wire that's kind of hanging loose. It's not attached to anything. No consistent flow of electrons can happen through those capacitors. So here we are charging, and we're just using the formulas for capacitors, C times V. We have a capacitor of 5 nanofarads and a battery with a voltage of 20 volts. That's going to give us 100 nanocoulombs of charge built up on that capacitor, and that's step one, is determining how much charge initially will be on capacitor 1. Now here we've moved the switch, so the switch now has gone from the left side over to the right side, and what we're going to do now is allow some of that charge to migrate. Now not all of it will go to the other side. What we're going to do is combine capacitor 2 and 3 together in series. So let's take a look at that. Here we are with combining those two capacitances together. C23 is going to be C2 times C3 over C2 plus C3. Now that's the same as the inverse formula that we've worked from. I just did a couple lines of algebra to flip capacitor C23 over, so it might be a little bit easier to work from. So in any case, those two capacitors in series give us a capacitance 3.94 nanofarads. So I've got 3.9 nanofarads on that side. Over here on capacitor 1, I have 5 nanofarads. There is not equal, but the capacitance on the two sides are sort of similar. And so what we're guessing is that we'll end up with similar amounts of charge on the two sides. There's not quite as much capacitance on Q23. It's probably not going to get as much charge. Now, charge is going to be conserved. So here is our statement of charge conservation. It says that the original amount of charge that we started with, the 100 nanocoulombs, will divide up between the two sides. And capacitor 1 will hold on to Q1 amount of charge, and let's say that the charge that goes over onto capacitors 2 and 3, we'll call that Q23. So what we can do then is we can say that because the voltages are going to match at equilibrium, that means that Q1 over C1 is equal to Q23 over C3. That equality of the two voltages is going to enable us to find out the ratio of the charges on the two sides. So we were able to show that charge 2, which is the same thing as charge 3, which is the same thing as charge 2,3, is equal to Q1 times C23 divided by C1. We could have added this, we could have listed this as Q23, that's what we did here in the notation. So to create better consistency, we could add a 2,3 onto that. All right, so we've got two conditions that need to be met. This condition of the voltages leads us to say what the ratio of charges needs to be. And then this statement of charge conservation. So we're going to combine those two to give us a formula that enables us to go in and calculate Q1. So Q1 turns out to be a portion of Q naught, of that 100 nanocoulombs. And the portion is going to be, simplifying this expression right there, is going to be C1 over C1 plus C23. Now if we go back in and do the very same calculation for the other side, for Q23, we're going to end up with C23 over C1 plus C23. It's got to be the case that these two charges combined, Q1 and Q23, combined equal Q naught. And we can see from those ratios, or from those expressions inside the parentheses, that will be the case. We also have to show that the ratios, if I take Q1 and divide by C1, it's got to equal Q23 divided by C23, and that condition is also met. So I think we're ready now. We can put some numbers in and see what we end up with. Putting the numbers in for the capacitances, I ended up with somewhere around 56% of the total charge staying on capacitor 1. So there's the 55.9 nanocoulombs. And then charge 2,3, we can now relax that back into charge 2 and charge 3. Right? Charge 2,3 is the same thing. They were in series. When we combine things in series, all the charges are the same. So charge 2 and charge 3 on those capacitors will be 44.1 nanocoulombs. Charge conservation, matching voltages on the two sides of the circuit. All right, let me know if you've got questions. Let's move on. So here is a second set of problems, a second midterm, 2, from a previous semester. And you guys can decide, were these kind of similar difficulty, or was one more difficult than the other? In this midterm, we're starting off with 3 objects, each with charge Q, each with mass M, placed into a equilateral triangle at distances L from apart from each other. So what we're going to do is they're all positively charged, and so we're going to hold them in place initially, and then we're going to let them go. So we're going to hold them in place initially and measure or calculate how much force is acting on each one of these. And then later in the problem, we're going to let go and use energy conservation, potential and kinetic energy formulas to determine how fast these things are going to be flying away from each other. So we need to get started with these forces. Now there's a lot of symmetry in the problem. If there were 3 charges and they all had different amounts of charge, if some were positive and negative, if all the distances between were different, we would have more things to calculate. But there's so much symmetry in this problem that there's a force acting between charges 1 and 2, there's a force acting between 1 and 3, there's a force acting between 2 and 3. Fortunately, the magnitude of each of those forces is identical. So we really just have to calculate one number for the force, kq squared over L squared, and that worked out to be 272,000 newtons. That's a lot of force. Let's see, we had 1,100 microcoulombs of charge. That's a pretty good amount. And they're separated by, 20 centimeters, something like that. So 272 kilonewtons of force. Oh, here we go. Calculate the force acting between any two of the objects. So they're kind of guiding us along here. Then in part B, it says, it may not get any more complicated than that. That's true. I was getting all set up to do a vector addition. But it turns out that they're not asking for net force. They're just saying how much force is acting between each pair. And so I did draw the net force in the diagrams, but I never ended up using those. All right, so we're ready to move on to part B. B says if we pick a point right at the center of that equilateral triangle, we're moving on to a calculation of the electric field. So, and it's asking us to explain our reasoning on this. Now, what will happen right at the center, again, we're working from the fact that there's a lot of symmetry here. We're going to have three electric field contributions right at the center at point A. They're going to be equal magnitude, and they're going to be equally spread out at 120 degrees to each other. And so we can use a symmetry argument to say three equally spaced vectors, angularly spaced, they're going to cancel out. Now, we could do a more complicated calculation to verify that, but if you've got a solid symmetry argument, then write that down, draw a diagram, and say, hey, the symmetry here means that these will cancel out. And that works. So making use of the symmetry in a problem is an important skill that you want to be developing. If the symmetry's not there, don't make that assumption. But if it is, use that in solving the problem. So I made the symmetry argument, I drew a diagram, equal magnitude, evenly spaced, and just wrote down the electric field is going to be 0. But you do need some kind of an explanation, it says, and that's what the diagram is doing. All right, for C, it says calculate the electric potential at the center. And of course, you guys know the easiest misconception to fall into here is that if the E field is 0, doesn't the potential have to be 0? And absolutely not. They're measuring two different things. Electric field is asking, if I brought a charge and placed it right at that center location, what would be the net force on that charge? And it would be 0. Forces cancel out and electric fields cancel out. They're vector quantities. But when we're asking about electric potential, what we're saying is, during the entire process of taking another charge and bringing it in from far, far away, from infinity and beyond, bringing it in and placing it at that center, it's asking how much energy or how much work would that require. And that clearly is going to require work. Bringing something in and placing it at that location is going to require some amount of energy. Now, once it's at that location, the net force is 0, and that's what the electric field is keeping track of. Now, to calculate the potential, it's a scalar, and so all I need to know is how much charge in each one of these surrounding charges and how much distance. So I can write that as 3 times kq. Now I'm writing this as kq over r because r is not the same thing as L. R is going to be the distance from the center of the equilateral triangle out to each one of the vertices. So we've got to do a little bit of trigonometry here. If we draw a diagram, I drew those lines in of r, each of those angles on the equilateral triangle are 60 degrees, and what we're doing is we're dividing them in half, so that's 30, and then I did an inverse cosine, or I divided through by the cosine of 30, and was able to show that r is 11.55. Now, this is a good place to stop and ask if that makes sense. Make sure you haven't lost a factor of 2, or Make sure you've gotten the angle correct. But 11.55 centimeters, that seems reasonable. The edges, around the sides are 20, and the R is going to be more than half that length. I can see from this, but not a lot more than half. So it seems like it's in the right size. All right, so I put the R in, calculated a contribution from each one of those, and got 257 times 10 to the 6 volts. So 257 megavolts of electric potential. That's a good electric potential. It's going to take a lot of energy, a lot of work to, again, bring a positive charge and bring it into that location. A negative charge would just sail right in, right? A negative charge would be pulled in very forcefully. Let's see how we're doing here. So I'm realizing what this problem is asking about is everything, right? It's asking about force, it's asking about electric field, it's asking about electric potential. So the only thing missing here is potential energy and, look at part D. Calculate the net electric potential energy of this system of charges. Now, if you remember, if we have a bunch of point charges out here, we can calculate potential energies by taking one pair at a time. So we'll say there's a potential energy due to the interaction of charges 1 and 2. There's a potential energy due to the interaction of charges 2 and 3, and then there's a potential energy due to the interactions of charges 1 and 3. Now, those are all the interactions, so those are the 3 terms that we have to add together. Now, even better, each one of those potential energy terms is identical. It's K, Q1, Q2, divided by distance. Now, the distance here is back to being L, and so I take 3 of those, and it says that the potential energy of building this system, not bringing in a 4th charge, but just bringing the 3 charges together, required us to do work of 163,000 joules. All right, really large force, 272 kilonewtons, really high potential at the center, and a really large potential energy in bringing everything together. All right, what happens now, part E, if all the charges are released, simultaneously, so we let go of them all, what will happen is they'll begin to experience a force. Now, this is where the net force does come into play. They're going to experience a force that pushes them directly away from point A. From point A, right at the center of that equilateral triangle, there's going to be a net force pushing them away. Now, it's not asking what the net force is. What it's saying is how much kinetic energy will each charge end up with, and then use that kinetic energy to calculate the velocity. So once the charges are several meters away, so we're treating this as all the potential energy will be turned into kinetic energy. By the time these have separated by several meters, initially they're 20 centimeters away from each other, we can use the approximation that all of the potential energy has gone into kinetic. Now, because of the symmetry in the problem, the kinetic energy is going to get divided up, or the potential energy is going to get divided up evenly. And so that's what we have here. Each one will acquire 1/3 of the total potential energy, and plugging those numbers in and then using the mass, we're able to determine that they're going to pick up a speed of 2,090 meters per second. They're going to accelerate to that speed as they move away from each other, and the force drops off pretty rapidly, and pretty soon all of that potential energy has been converted to kinetic. All right. So watch for symmetry in problems. It can make a problem pretty straightforward. You can answer, if you've got a lot of symmetry, sometimes things are going to go much faster. All right, let's look at problem 2. Now, problem 2 here looks like another Gauss's law problem. A very long hollow plastic. Now this is a cylinder. Now this is a bit of an issue with drawing cylinders and drawing spheres. They look the same. So read carefully. If you look at the diagram and it's round like this, remind yourself, ooh, is that a sphere or is that a cylinder? Could be either one. So here it says that it's a cylinder, it's an insulator, and we've placed charge on it. So the charge is uniformly spread through that gray material that we've listed here. So they want to come up with a formula for the electric field everywhere around this. Now, we've worked with Gauss's law, and we've said that spheres are great, because when we use Gauss's law with spheres, we get the exact answer. With cylinders, not necessarily. Cylinders only work well if the length is much bigger than the radius. So we're going to assume that L is quite a bit larger than A or B. Those are the two radiuses that I've introduced here. And even then, Gauss's law is only going to work well as long as I stay pretty close to the surface. If you were a little tiny bug crawling along, a ladybug crawling around on this surface, looking out, it might look infinite to you. But if you get a little bigger and you look out, or if you step away from the cylinder, at some point you're going to go, oh, it looked infinite, but it wasn't really. So Gauss's law is only going to work in those regions where the little tiny, bug was able to look around and it looked infinite. Okay. So let's use Gauss's law. Let's pick some Gaussian surfaces. And the Gaussian surfaces this time are going to be cylinders. Now I can draw a Gaussian surface within that inner surface, and I can draw a Gaussian surface that completely wraps around the cylinder, and then I can pick a Gaussian surface in the region between the two cylinders. Okay. And so, or within the cylinder material itself, let's call it that. So there's a region inside that's hollow, there's a region of the cylindrical material itself, and then there's a region outside. So what I'm going to do is I'm going to solve part A and, was it B? Yeah. Okay, yeah, I was thinking they did it from starting inside out, but they actually did the easiest region, and then the next easiest region, and then the really complicated region. So inside's not so difficult. If I'm doing a cylindrical Gaussian surface inside, it hasn't enclosed any charge, and the electric field is going to be zero everywhere along that surface. When we move on and go outside the surface, at that point we will have enclosed all of the charge. Now for cylinders, the left side of Gauss's law always reduces down to E times 2 pi RL, because that's the surface area of the rounded portion, and that's where the electric field is directed across the Gaussian surface. So I put in the 2 pi RL, set that equal to the 4 pi K times the enclosed charge, and ended up with an electric field that's 2KQ over L, 1 over R. Okay, here's the hard one. So in the region in between, I can still use cylindrical geometry. So the left side of the equation looks just like the left side did over here. But now I've got to calculate Q enclosed, and it's not going to be easy. Q enclosed is not going to be the total Q, depending on where we draw the Gaussian surface. Q enclosed is going to be a fraction of the total charge, and it's going to be the enclosed region, pi r squared minus pi a squared, over the total area of that region. Now, there's a factor of L, top and bottom here, but those have both canceled out. So this is giving us the fraction of the total. We can try this out. What happens when little r is equal to A? Well, when little r is equal to A, we haven't enclosed any charge, right? So we start with a Gaussian surface right at r is equal to A, And then we let that get bigger and it makes its way to the outside. Let's stop it at some intermediate region, and that's what we're trying to calculate. Now, if we let that continue all the way to the outer region, what does this formula say happens when r is equal to b? And when r is equal to b, we've enclosed all the charge. So we've used these cross-sectional area formulas, and again, you could put a factor of L, top and bottom, and turn them into volumes, and start from that step. So if I go back to this statement from Gauss's law, and divide through by 2 pi RL, that's it. This is the formula we get. And I left it in a form where it looks kind of like the Q that we had for outside. I just took that factor of r squared minus a squared over b squared minus a squared and put that in. To me, that's a geometric reminder of how this is all working. All right. And the function's a little complicated, right? It's r squared minus a squared over r, so it's going to have a linear part to it, it's going to have a 1 over r part to it. We could graph that or something and see how the electric field varies. All right, let's move on. Problem 3. Problem 3 says that we've got a disk. So we've got point A, we have a uniformly charged disk of radius r, total charge q, I need to write a q in right here, and we want to find out as a distance of x. So we move along the x-axis, and we're going to treat x equals 0 as being right at the center of that disk. As we move along the axis, what is the electric potential? So they're finding the electric potential at every location along the x-axis. Okay, so it's calculating the electric potential at all the different possible regions along the x-axis. It's not doing the electric field, they are doing the electric potential. So as always, the good news here is that the electric potential is a scalar. So let's take a look at that. Here we go, it's the very same setup that we had shown. Now x we're using as this horizontal distance. Little r, because we have a disk that we're integrating, I'm using little r to represent the different radiuses of the disk. We're going to use a series of circular strands, so circular loops, and we're going to integrate all of those together, all of the effects. Now, dV, a little bit of potential, is going to be created by the little bit of charge in each one of those circular loops that we have. So k dq, and the distance is going to be x squared plus r squared over 1/2. So the dq now, if we break the charge down into how much charge is on each one of these circular loops that we're going to be integrating, the loops have an area, 2 pi r all the way around with a thickness of dr, and the area of the entire disk is pi r squared. So again, the charge was uniformly distributed, and that would be the fraction of the total charge contained in each of those infinitesimal loops. All right, so the integral looks like this. So it actually looks like this down here. But what we've done is we've got 2kq r squared r dr over r squared plus r squared to the half, x squared plus r squared to the half. One way we could solve that is to define a variable, we could do a variable switch. So I'm going to use the variable u to represent x squared plus r squared, and then du would be dr r squared. And since we already have an r dr on top, that's going to fit perfectly. This is one of those techniques, you know, in Calculus 3b, one of these integration techniques. And so this particular integral is not too difficult. We should be able to solve for that. So I made the substitutions, and I plugged everything into the integral here, and it turned out to be du over u to the half. Okay, and so du over u to the half is not too difficult to integrate also. What I'm going to integrate that out to be is u to the half, 2 times u to the half, and then I have the limits of integration as to what u will be equal to at those limits. So that's it. That's the electric potential that we've calculated. So I've got V as a function of x at all locations along the x-axis. Okay. Now, the questions they ask, a couple questions, not this one, this one. By the time I get to x equals 0, what's the potential? What would be the potential if we integrate all the way towards the to that point where x is equal to 0? What are we going to get? And if we plug in 0 for x, we get at the center a potential of 2kq over r. So you can see integrating to the surface of a disk is twice as much potential as the potential on the surface of a sphere with the same radius. In this case, looking at a location right along the surface of the sphere means that you're very close to well, I guess you're closer on average to the charge than if you're sitting at the surface of a sphere. If you're looking at a sphere, the charge wraps away from you. Here, the most distance charge is r. But that's kind of interesting. You get something with just a factor of 2 from some of the formulas we've seen for spherical shapes. This is a different shape. We would expect it to be a different formula. Finally, for C, it says, what happens now if we move all the way along the x direction out towards infinity and beyond? What will the potential be? Now, you guys know from what we've done in physics and what you've done in your calculus classes, they're not asking us to say it's 0. They're asking us to say, is there a way we can approximate the function to represent how it's behaving at long distances? So kind of the standard technique we've been using. In this case, we're taking the complicated part of the formula of the function. In our case, it's this x squared plus r squared to the half. And we're going to allow x to get really large compared with r. And so I'm going to factor out the big part. That leaves us a factor of 1 plus r squared over x squared to the 1/2 power. And using that approximation, which was given, so in the midterm, that approximation actually is right here. We use that in a number of examples. These are some good chances. These are some good opportunities to go in and practice some of these techniques that we've learned in physics and that you've seen in your calculus classes too, to use approximate formulas for some of these extreme values of x. And so I factored that out, and then I used the approximation technique. That went to 1 plus, the power here is 1/2, and the tiny number is r squared plus r squared divided by r squared, but divided by x squared. And so the potential that I'm getting here, 2kq over r squared, I've got an x plus 1/2 r squared over x when I multiply that through. The x's, the big pieces, cancel out. And so what we're left with is kq, and the r squareds cancel too, kq over x. And kq over x looks like we're back to a point charge formula. I think we did 2 or 3 examples with electric fields. I'm not sure. I guess we might have done some with electric potential too. But we know that if we get far enough away from any charge distribution, it starts to look like a point charge, right? It starts to look like you get so far away, any shape charge distribution turns into the potential or the electric field of a point charge. Let's take a look at that last problem. So here is our chapter 24 problem, and here we are looking at a system of capacitors, 9 volts. Now I can see that I've got a couple capacitors in series right there. I have another couple capacitors in series right there, and that once we combine those two into one capacitor, and we combine those two into one capacitor, those two remaining capacitors will be in parallel. So definitely practice this series and parallel capacitor solving. I've got the 9 volts here. So capacitors, I think I'm going to start calling that capacitor 1 and 2. Let me see if that's what I called them. Yeah, I did. So capacitor 1 and 2, they're going to be sharing voltage. Neither one is going to get the full 9 volts. Capacitor 3 and 4, the same thing. They are going to be sharing voltages. So what I wrote was that if I look at the voltage across capacitors 1 and 2, it's going to be 9 volts. And if I look at the voltages across capacitor 3 and 4, that's also going to be 9 volts. So we can combine capacitors 1 and 2. And I've used that, what I'm going to say is kind of a shortcut formula. Instead of putting everything as inverses, if I just have 2 capacitors, C1, 2 is in series, C1, C2 over C1 plus C2. And then it saves me from doing the inverse. Maybe it's not a shortcut. Maybe it's to avoid errors. Anyway, I ended up with 12 nanofarads as the combined capacitance. Now, if I've done this correctly, what I've got for the combined capacitance should be less than either C1 or C2. Now, that worked. It doesn't guarantee that what we've done is correct, but that is a way to check and see if there's an obvious error that has happened. So once I get those capacitance, then I can go in and calculate charges. Q1 is going to equal Q2 because they're in series. I'll just call that Q12. That's going to be C12 times voltage 12. So I didn't really have to combine all capacitors into one. I was able to just combine those 2 capacitors, and at that point I already knew that the total voltage would be 9 volts across just those 2 capacitors by themselves. So I didn't have to go in and combine everything together. So Q1 equals Q2, and using those numbers tells us it's going to be 100 nanocoulombs. So that's charges Q1 and Q2. Now, charges 3 and 4 work the very same way. So we can combine those 2 capacitors that are in series. We got 24 nanofarads. That's less than either one of those. It's a good sign. It means that we may be on the right path. And then I can use formulas for calculating the charge on 3 and 4 by using this combined C34 along with the combined voltage. So Q3 and Q4 have 216 nanocoulombs to them. Now it also wanted all the voltages. We got all the charges. They want all the voltages, and I can get the voltages one by one now by taking these charges and dividing through by the corresponding capacitance. I ended up with 3.60, 5.40. Oh look, 5.40, 3.60. Now what should be true, when you can find places to double check. And if you see a problem, but you can't track it down, first thing is if I identify that I've done something wrong with one of these checks, go back and see if you can correct it. If you're running out of time on a midterm, for example, and you can't find the error, write a quick note and say, these 2 voltages should add up to 9, but they don't. Now in this case, it looks correct because they do add up to 9 volts. And these 2 also add up to 9 volts. Now the last thing it asked for was the potential energy, the energy stored in the capacitor. And the energy stored, we said, is given by 1/2 QV. We went through the derivation and showed why there's a factor of 1/2. So, in these type of problems, often students will leave the 1/2 out, and that's not correct. And you should understand why the 1/2 is there. So using the formulas, I went through and calculated the energies. Let's see, the Q's were in nanocoulombs, the potentials were in volts. The energies ended up being in nanojoules. Looking to see if those seem sensible, and it looks like they do. They sort of make sense. Okay, so those are the energies stored in the capacitor. All right, I hope that with these practice midterms, these sampler midterms, they're providing a good way to go in and get a feel for what a set of problems on a midterm might look like in terms of how difficult the problem's going to be. So which midterm do you think was easier or harder, or were they comparable? Kind of leaning, well, there was that problem though. Not sure. I'm leaning towards the second one being a little more difficult overall. So, and you know, students always feel like whichever midterm they've taken was the hardest of all the midterms they've ever seen. So that's just something that happens. So again, any of these questions, you know, during the reviews, we're not able to sample everything that we've done. I think we've done a pretty good job though. If you look at some of these problems, they're sampling a lot of different concepts from each of the 4 chapters. So I think it's a good overview. But so definitely take a look at these, practice them, think in terms of what are you learning from the problems and how would this apply to a new situation that you would encounter. So, and then make sure you're looking at homework problems also, and then examples from lecture. I know it's a lot to go over, so get an early start. I hope you guys have gotten an early start in going back and reviewing through these problems. All right, I will see you all in office hours.